In this video, we're going to discuss the IB simple harmonic motion kinematic equations. We're going to explain where they come from, and we're going to show you how to use them and which equations they give you on the test and which ones you have to memorize. Okay, before we start, you need to know a couple of things. First, it's really important that you remember that the IB notation for amplitude and max displacement is different than that of on an AP test or most American books. X naught often represents initial velocity in most American books and AP textbooks, but in IB, X sub zero or X naught represents maximum displacement. And so the sub-zero, I'm not sure why, but the sub-zero to them represents maximum. So V naught is maximum velocity and A naught is maximum acceleration. Also, we're going to be using the equations for position, for simple harmonic motion for position today, so don't forget them. All right, so in class, what we did is we took a simple harmonic motion position versus time graph, this particular one here, and we analyzed it and we tried to create a velocity versus time graph so we could see what that equation would look like. You had to figure out different things, the amplitude here, or the max displacement, which is 0.2, and the angular frequency, which you can figure out from the period. Period is 25, right? And from there you can calculate, as shown above, what the angular frequency is. The function that goes along with this should be something like this, x equals 0.2, which is the maximum displacement, times sine of omega t, where omega is the value we calculated. Now, the important thing that you recognize is that from a position versus time graph, you can actually figure out the shape of the velocity versus time graph by just using plain induction. We know that the velocity versus time graph is, or the velocity at any time will be equal to the slope or instantaneous rate of change on your position versus time graph. So if I drew a tangent line at different locations and found the slope of those tangent lines at different times, I could find the velocities at all those times. Now, looking at this here, we could just see, hey, this is where the graph is the steepest is always when it crosses the x-axis. So that will be always the maximum velocity. So at the beginning, it's at its maximum velocity, because it's the steepest, and it's in the positive direction. That means the velocity time graph will start at its maximum up here, and then it'll come down to 0, and then it'll speed back up in the negative direction, then slow down and come to 0, and then speed back up in the positive direction. So it will start at its positive value, maximum positive value, and then wiggle, which means it's going to be a cosine function in shape. So we can always do this with any graph, figure out the general shape of the velocity time graph. And that's an important skill to have. So like we predicted, this is the shape of the velocity versus time graph if we found the slope of the position at lots of different locations. The main one that we need to find is the maximum velocity, which looks like we calculated the maximum velocity, V naught, to be around 0.05. If you figure out the angular frequency for this motion, the period appears to be the exact same as the period for the previous graph. So therefore the frequency will also be the same, and so will the angular frequency. So 0.05 is the maximum velocity here, or the mathematical amplitude of this graph, and the angular frequency is the same value. The equation would look something like this. It's a cosine function, but instead of x naught for your the value in front, it's now V naught, right? And this mathematical amplitude is no longer the maximum displacement, but the maximum velocity. Now, one really ridiculously important note that you should be aware of that confuses a lot of students is the term amplitude. Amplitude is both a mathematical term and a physics term. It's important you know the difference between them. Amplitude, mathematically, is simply the distance from equilibrium, or the x-axis, to the maximum value or the minimum value. And both of these graphs have amplitudes. However, physics is math with meaning, and the meaning of this distance here is the maximum displacement, which is 0.2. The meaning of this mathematical amplitude is the maximum velocity. When we say the word amplitude in physics, though, we mean only one of these because they're both amplitudes. So when we say amplitude, we actually mean specifically the maximum displacement. We don't mean maximum velocity. If ever something asks find the amplitude, they mean find the maximum displacement, not the maximum velocity. So even though the velocity time graph does have an amplitude, a mathematical one, we don't call it that. All right, keep that in mind. All right, so how do we find the maximum velocity? If I wanted to quickly know what the equation was for a velocity time graph, if the position versus time graph is a sine, we can see that the velocity versus time graph would be cosine. It would have the same angular frequency, but what would v not be? The only way we figured out from our experiment that it's 0.05 is by finding the slope at different points and figuring it out that way. That's going to be a tedious process. Hopefully there's a faster mathematical way, and there is. If you look at these values here, the maximum displacement and omega. Omega is around 1/4 or 0.25. Maximum displacement is 0.2. How can I combine these two numbers to get 0.05? Well, if I multiply them, 1/4 of 0.2 is 0.05. So it turns out that the maximum velocity is equal to the maximum displacement times the angular frequency, or v naught is equal to x naught times omega. This equation is ridiculously important and you will use frequently. You must memorize this equation though, because they don't give it to you on the test. You need to remember this. This is vital that you remember this equation. All right, what about the acceleration versus time graph? If I wanted to find out the shape of an acceleration versus time graph, I would also want to think of the velocity versus time graph. Unfortunately, I don't have it right here, so I'm going to try and draw it with my cursor here. It was a cosine function, was the velocity versus time graph, right? So it started at its maximum value and then wiggled, okay? What would the acceleration look like? Well, acceleration is the slope on velocity time graph, right? So on the cosine, right, when it starts at its maximum, the slope is 0 at first. That means it's going to be 0 acceleration at first. But then the slope goes downward, so it becomes a negative slope. So while it starts at 0 and therefore is a sine function, it actually goes downward, and so the acceleration time graph appears to be a negative sine function. If you are careful in finding your slopes and things like that, we get the acceleration to be around 0.013, and hopefully you found something similar on your lab. And then the function would look something like this, right, where it's a negative sine function, and the mathematical amplitude is now represented by the maximum acceleration. So how do we actually find mathematically the maximum acceleration? How can we mathematically find 0.013? Well, we tried last time. We multiplied max displacement by angular frequency. Let's try the same thing again. Let's multiply this time max velocity, by angular frequency and see what we get. 0.05, a quarter of 0.05 is 0.0125, which is really close to 0.013. And so it sounds reasonable that the maximum acceleration would be equal to the maximum velocity times your angular frequency. So this sounds pretty good. It sounds like it would work. However, we could put it in terms of maximum position or displacement instead of maximum velocity. Remember, maximum velocity was maximum position times omega. So if we take and substitute maximum position times omega in here, there'll be 2 omegas, and this becomes maximum acceleration equals maximum displacement times omega squared. All right, well, we're actually going to simplify this a little bit more. We're going to take this, and we're going to do something with this here in just a second. Remember the equation, the general equation for acceleration we found was acceleration equals negative max acceleration times sine omega t. So let's take this quantity here, since this quantity equals max acceleration. We'll plug it in here. We get something like this. If you'll recall, this right here should hopefully look a little familiar. max displacement times sine of omega t. Remember, that was our original equation for the position time graph, right? This right here, therefore, equals position. This right here can be gotten rid of and just represented solely by x, or wherever the object is, which means the final equation for acceleration can be written as acceleration equals negative omega squared times x. You should recognize this because this is the defining equation of simple harmonic motion. And this equation shows, right, that all the functions before must be perfect sine and cosine graphs. The equation for sine can be used like this, the equation for acceleration can be used in this form, it can be used in this form, or it can be used in this form. They all work, okay? We're going to often write and talk about it in this form. And if you ever want to use this, and let's say you want to find the acceleration at a specific time, just use this equation for position. Find out where you are at that time, and then plug it in and find out what the acceleration is. All right, so let's quickly summarize the different equations we have so far. We have our position versus time graph, which was a sine graph. The velocity versus time graph, because it starts off at its maximum slope, this is maximum velocity, and therefore is a cosine function. And then the acceleration, we can see it's flat at first, right? So zero slope of velocity, that means zero acceleration, and then goes negative. So this acceleration graph is a negative sine function. And these are the corresponding equations that go along with it, where if I took this and substituted it in for x, it would be a negative sine function. So these are the equations that we know, and we need to just simply remember that when we're calculating max velocity is equal to max displacement times omega. This is all useful, and we're going to use this many times. However, remember there were two different equations for position. What if the position equation that we had, or function we had for a problem, was the cosine one, not the sine one? What would we do then? Well, let's take a look. If it's a cosine function, what would the shape of the velocity time graph be? Well, here we have a zero velocity or zero slope, so this should start off as zero velocity, and then the slope becomes negative. So this we could figure out, oh, this must be a sine graph, starts at zero and then goes down, but it's a negative sine graph. Okay, so we know the shape now of this velocity. If your position is a cosine function, your velocity will be a negative sine function. And let's take a look at this one and see what the acceleration should be. If the slope is a maximum here, that means this will be a maximum, but this is a negative slope, maximum negative. That means this will be a maximum negative value, so this looks like a negative cosine function. That starts from here. So while your position is a positive cosine function, your acceleration or your velocity will be a negative sine function, and your acceleration will be a negative cosine function. If you took all this, substitute in for x, it's negative cosine. So we can see here that these are the different equations in the two different scenarios. Let's summarize it all up together. These are all the equations that we've talked about thus far. And this is how they list it on the IB test itself. These equations right here, these four, are given to you on the test, and they write it out exactly like this. These two equations are not given to you and are ridiculously important, so please memorize them. Now, the way this works and how you can tell which equation you use when is first think about the motion and decide, okay, is this motion is the position time graph going to be sine or cosine? Decide that. If it turns out to be sine, the corresponding velocity equation is the one right below it. So these two are paired together. When your position is a sine function, your velocity is a cosine. And these two are paired together. When your position is a cosine function, your velocity will be a negative sine function. And you can use this method to always remember the equation or the shape of the equation for your position and your velocity. If you want to know acceleration, you've just got to remember this equation. Plug in your position versus time. If this is your position versus time is a sine, plug it in here and it'll be negative sine. If your position versus time is cosine, plug this position into this right here, and it'll be negative cosine. And that way you can know the shape of each of your graphs and their equations. Just make sure that you memorize these two equations.